Hi, in this session we are going to discuss about convective heat transfer. So as we have discussed, convective heat transfer is a mode of heat transfer between solid and liquid. Let us say this is a solid surface of temperature Ts and a liquid is flowing over this surface whose uniform temperature is T infinity. And let us say this is the fluid of uniform temperature T infinity. Then by Newton's law of cooling, heat convected, that means heat can flow from solid to liquid or liquid to solid. So q dot convection is nothing but HAS Ts minus T infinity, where H is convective heat transfer coefficient and A is surface area through which heat transfer is taking place. So the convection or convective heat transfer is of two types. Convection is of two types: free convection and forced convection. Forced convection. So free convection is when fluid flows due to density variation. Then the heat transfer between solid and liquid is known as free convection. If and the in forced convection, when fluid is forced to flow by any external means such as fan or blower, then the convective heat transfer is known as forced convection. So if we consider a situation, let us say this is a solid surface, okay, and its temperature is Ts, and the surrounding air is at temperature T infinity, and there is no external means which is forcing this air to flow over the surface. So what will happen here is, let us say Ts is greater than T infinity. So there will be some amount of heat transfer from solid to air, and this air will gets heated, and hence density will reduce. So this air will go upward due to density variation, and cooler air from upper side will come and try to get the heat from surface. This is the free convection. And consider one another situation in which fluid, this is the surface whose temperature is Ts, and a surrounding air is forced to flow by a fan. So it is flowing like this, in this direction. Okay, fluid is flowing. So this kind of heat transfer is known as forced convective heat transfer. Let us consider a situation in which fluid is flowing over a surface. Okay, this is a surface. If the fluid is flowing over the surface, let us say the free stream velocity of fluid is u infinity. Then as soon as the liquid comes into the contact of the surface, its velocity goes to 0. This velocity u goes to 0, and as it moves on the surface, its velocity increases and increases. So the flow region, or we can say flow region adjacent to the surface, in which viscous effect are dominant, is called velocity boundary layer. Velocity boundary layer. Okay, and the reason for development of velocity boundary layer is no slip condition. That is, the fluid layer adjacent to surface will come to rest. So, due to no slip condition, at the leading edge velocity goes to 0, and as we move this side, velocity will increase. So this region is known as the boundary layer. Okay, so the thickness of boundary layer, thickness of velocity boundary layer, let us say we denote this by delta. It is defined as the distance y. If we say this is our y and this is x, this is x, this is y, the distance y above surface at which velocity of fluid particle becomes 0.99 of free stream velocity is what? Thickness of boundary layer. An implication of no slip condition is that all the heat transfer from the solid surface to the fluid layer adjacent to the surface is by pure conduction. So from here to adjacent layer, very adjacent layer, the heat transfer is taking place due to pure conduction. So Q dot convection at the interface of solid and liquid is same as heat transfer due to conduction is equal to minus K fluid into del T upon del Y at Y is equal to 0, where K fluid is nothing but thermal conductivity of fluid. T is the temperature distribution inside the liquid. Since at the interface Q dot conduction is equal to Q dot convection, so we can write H Ts minus T infinity is equal to minus K del T upon del Y at Y is equal to 0. Remember, this thermal conductivity is of fluid. So the convective heat transfer coefficient H can be given as minus K fluid del T upon del Y at Y is equal to 0 upon Ts minus T infinity. This is one of the important relationship. Okay, this is important. There are many parameters on which heat transfer coefficient H depends. So to reduce the number of variables, we define a various dimensionless quantities, or we can say dimensionless numbers. So our next topic is dimensionless numbers. Okay, in which we will first study the Nusselt number. Nusselt number is also known as dimensionless heat transfer coefficient. So the Nusselt number Nu is defined as rate of heat transfer due to convection upon rate of heat transfer due to conduction. So if we write Q dot conduction or convection, it can be given as H into delta T. Let us say delta T is the temperature difference between the solid and liquid. Delta T is temperature difference between solid surface and liquid, and the heat transfer due to conduction at the interface, it can be written as K delta T upon L. Okay, so if we take the ratio of these two, we will get Nusselt number is equal to HL upon K. Okay, so H is the, as usual, convective heat transfer coefficient. L is known as characteristic length. Characteristic length, and it is defined as 4 times cross sectional area upon weighted perimeter. Weighted perimeter. And K is nothing but thermal conductivity of fluid. So if Nusselt number is equal to 1, that is heat transfer is only due to conduction. Okay, the second dimensionless number is Prandtl number, which is denoted by PR. Prandtl number is defined as molecular diffusivity of momentum over molecular diffusivity of heat. Molecular diffusivity of heat, which gives us mu Cp upon K. If you see here, For gases, for gases, Prandtl number is approximately equal to 1. For liquid metals, Prandtl number is less than 1, and for oils, Prandtl number is greater than 1. So there comes one relationship one relationship between velocity boundary layer and thermal boundary layer. Velocity boundary layer and thermal boundary layer. If we see here, this is given as velocity boundary layer is equal to thermal boundary layer into Prandtl number to the power 1 by 3, or we can write this hydrodynamic boundary layer thickness over thermal boundary layer thickness is equal to Prandtl to the power 1 by 3. This is again important. Okay, you can derive this. I am not deriving because it is not going to come in the GATE exam. You have to remember only this formula. So from here we can say if Prandtl number is less than 1, this implies the thermal boundary layer thickness is greater than hydrodynamic boundary layer, and if Prandtl number is greater than 1, this implies the thermal boundary layer thickness is less than velocity boundary layer. This is also important. And the third dimensionless number is the Stanton number, which is denoted by St, and it is given as H upon rho Cp V, where H is the convective heat transfer coefficient, rho is the density, Cp is the specific heat, and V is the velocity of fluid. And this further can be simplified as Nusselt number upon Reynolds number into Prandtl number. So this is another form for Stanton number. Now we will discuss the heat transfer from a flat plate, or we can say the next topic is flow over flat plate. As we have discussed, the heat transfer is dependent upon type of flow. So the type of flow, how we will differentiate that one flow is laminar and the other is turbulent. How? So Reynolds number gives us that whether a flow is laminar or turbulent. Okay, let us say this is a surface and a fluid is flowing over this surface whose uniform temperature is T infinity. Let us say this is a fluid. Now, so due to no slip condition, there will be one boundary layer generation, turbulent region, right? So this region, there will be one turbulent flow, one laminar flow. So this is, let us say this is laminar region. After laminar, we will have one transition region, and the final one will be the turbulent region. So in laminar flows, a flow will be laminar over a flat plate if Reynolds number is less than 5 into 10 to the power 5. Okay, flow will be laminar. If Reynolds number is greater than 5 into 10 to the power 5, flow is turbulent. And this Reynolds number is nothing but rho v x upon mu. Okay, so for laminar flow over a flat surface, the thickness of hydrodynamic boundary layer is given as 4.91 x upon root of Reynolds number at a distance x, and the Nusselt number nux at a distance x is given as 0.332 Reynolds number at distance x to the power 0.5 into Prandtl to the power 1 by 3. Similarly, if the flow is turbulent, for turbulent flow over a flat plate or surface, velocity boundary layer thickness delta is given as 0.38 x upon Rex to the power 1 by 5, and the Nusselt number at a distance x is given as 0.0296 into Reynolds number to the power 0.8 into Prandtl to the power 1 by 3. This is important. This is important. Okay, you need to remember this. Now, if we say the convection is of forced type or forced convection, then the Nusselt number nu at x is given as 0.332 Prandtl to the power 1 by 3 if the flow is laminar and surface is at uniform temperature, and the average heat transfer coefficient HL upon K, this is equal to 0.664 Reynolds number over the whole plate to the power 0.5 into Prandtl to the power 1 by 5. Important. And NUX is nothing but convective heat transfer coefficient at a distance x into x upon K. This x is nothing but the local heat transfer coefficient. Okay, now, and this is when the flow is laminar and surface is at uniform temperature. Now, if flow is turbulent, then Nusselt number nux local Nusselt number is given as 0.0296 into Prandtl to the power 1 by 3 Reynolds to the power 0.8. Turbulent flow and uniform temperature. Okay, and the local Nusselt number NUL is HL upon K is equal to Reynolds number over the whole plate to the power 0.8 into Prandtl to the power 1 by 3 when turbulent flow over entire flat plate and uniform surface temperature.